See, I fill the rows in this order and dua on it. But this is okay. Sembilan, sini, dua, sini, tetapi it is too small. Terkecil? Terlalu kecil? Better. Okay. So I will sift up. Enam, di mana? Di dalam tiga. Lima?
Bawahnya tiga.
See. Okay. Now, how expensive is insert? If I have n elements here, how many steps to insert? I always know where to put it. That's one step. But it might sift up all the way. Lantai. Pertama lantai, kedua lantai, ketiga. Now, how many? Berapa lantai? Here, 4. But if I have n elements, how many?
Terhingga.
Not n. Here I have 9 elements, but only 4 lantai. So, what is the connection? So, the number of rows equals some function of n. What function is it? I will tell you the exact answer. The exact answer is the ceiling of the log of n plus 1. But no, of n plus 1. The exact number is not important. Ceiling means if it's between two integers, move up to the next integer. So, when I say log, I mean logarithm base 2. In computer science, log is always base 2. In engineering, in physics, logarithm is always base 10. In mathematics, logarithm is always base n. But computer science, you don't need to say, but I mean log 2. Well, this then is order of log of n. That is insert, the cost of insert. Now let us try delete. In a priority queue, we always delete the root. This is a kind of tree. Pohan. Now, in the forest, the pohan grows like this. In computer science, the pohan grows like this, starting here and growing down. This then is the root. These are the down, the leaves of the tree. So, we always delete the smallest element. And the smallest element is always at the top because of our rule. So when I delete, that is the element I delete. This is a priority queue. Each number might represent importance. Small numbers very important, large numbers not important. when I put them in, I build a heap. When I take them out, I always want the most important number out now. And so 1 is the most important number. But now it is no longer a good heap. It has lost its root. How can I fix this? I could take everything out and put them all in again. Very expensive. Instead, I will take the very last element, lima, and put it here. Now the shape is right. The shape is right, but the numbers are bad because orantua terlalu besar. But I can now let it sift down. I can move it down atau ke kiri atau ke kanan. Which is better? How many people say kiri? How many say kanan? How many people don't say? Well, let us try kanan. Is it good now? No, because this now is just as bad. So one answer is really better. Always go to the child that is smaller. 1 is smaller, is better. So we always sift to the better side. Now, is this good?
No.
No, belum. Shift ke kiri ke kanan. Ke kiri. Sudah baik?
Baik.
Baik. Let us now delete again. What do I do to fill the empty space? Ya, enam. Ke kiri, ke kanan,
Kanan.
ke kanan. Ke kiri, ke kanan,
Kanan.
ke kanan. Ke kiri, ke kanan. No need. Okay, good. One more time. 2. Well, you see the idea. What is the cost of delete? Well, I take something off, 1 step. I put something in its place, 1 step. I then sift down. How many steps? How many lantai? Now it's 3, but if I have n elements, how many lantai? Not 3. If n is 1,000, it is not 3 tiga lantai. Berapa lantai ada jika n ialah 1,000? Sepuluh. So what is the formula? Berapa lantai? Number of rows equals some function of n. What function? Log. Yes. Delete costs logarithm. Now, I can use this to sort numbers. I have many numbers. To sort them, I first build a heap. Then I take the numbers out of the heap. They come out in order. How expensive is sorting using this method? Well, a little bit more complicated. I have n numbers. As I put them in, the cost gets more and more for each number until the last one costs log n to insert. So I have the last insert costs log n. The previous one I will overestimate and say it's also log n. It's close. And the one before that is also log n. I will say that each number costs log n, and I have n of those. That is an estimate. How expensive is it to build the heap? And now, as I take elements out of the heap, the first delete certainly costs log n, but now it is a little bit smaller, my heap. So the next delete is also log n, and I must delete n times. And the last one only costs 1, but I will call it log n also. So how much does that add up to? I have n times log n plus another n times log n. So that's 2n log n. It's an estimate, an overestimate, an upper estimate. That is order of, good. These are all very small. Now with 2, this stays 1. In fact, this is always 1. Log of 2 is 1. And this, of course, is just n, so 2, 3, well, I'll do those eventually. N log n is 2, n squared is 4. Now with 3, again, it's small. Log is 1.6 or so. It's not big. N is 3. N log n is about 5. N squared is 9. When I get to 10, let me move it down a bit here. 10, log of 10 is approximately 3. Now the next one I want is 100, I think. I will skip 20. 100. Log of 100 is approximately 7. And the last one I'll do here is just 1,000. Log of 1,000 is approximately 10. Okay, so if my method is log n, it is not very expensive, even for big numbers. It is much better than order n. And order n is much better than n log n. And both of those are much better than n squared. So you try to make your algorithm as fast as possible by making it as close to the left as you can here. You do not want n squared algorithms if you can use an n log n algorithm. Now, what I just showed you was heap sort, sorting using a heap. This is called a heap. Come back in a second. My computer timed out. The priority queue is also called a heap. And for some reason it's not. Doesn't make any difference. I'm using the board. So heap sort is n log n. Do you know any other sorting method besides heap sort? How would you sort numbers? Maybe you know bubble sort. Bubble sort is n squared. Much, much worse. Never use bubble sort. Binary trees. Again, same numbers. Now I will insert these numbers into a different data structure. Here is an empty binary tree. Oh, before I finish that, one more thing about heaps. Do you actually represent them as trees? And the answer is no. You can actually represent a heap in an array, starting at location 1. So if you have this heap, for example, you would just store it this way. Whenever you insert, you always insert in the next location, because that is the next location. When you need to sift up, you need to find the parent. The parent of the element at Anam is at Anam divided by 2. Here it is. That is the parent. So I know how to sift it because I know exactly where the parent is, where the orang tua is. And the orang tua of 3 is 3 divided by 2, which is 1. There is the orang tua. So I don't need any pointers. It is all in an array. And to find the children, which I need for sifting down, where are the children of this? They are here and here. This is location 3, location Anam, dan tuju. So this is the way to actually represent a heap in the computer. Okay, now, binary trees. Empty binary tree, put in the 3. It looks like that. Looks just like a heap. It is different. Put in the 1, it is here. 4, it is here. All right? 1 is here. That is not like a heap. Lima, here. Now I am following a rule. Can you discover my method? Sembilan, sini. Dua, sini. Anam, sini. Dan 5, sini. All right, where would I put kasa? Where? Here. Where would I put, let's see. Where would I put this number, 3.5?
4.
Here. Here is my rule. Let me put in the number 7. To insert 7, I start here. And I say, is 7 bigger or smaller? Bigger. Go to the right. Kakana. Bigger or smaller? Bigger. Kakana. Bigger or smaller? Bigger. Kakana. Bigger or smaller?
Smaller.
Smaller. Kakiri. Bigger or smaller?
Bigger.
Bigger. Kakana. Open space. So if I use this arrangement, the numbers are actually sorted. Here they are. If I read this way, no, 1, 1, 2, 3, 3.5, 4, 5, 5, 6, 7, 9. Reading it in this order. So this is called a binary tree. Pohon binar. How expensive is it to insert? Well, I might need to go to the very bottom. How many levels? Well, maybe the tree is very nice and balanced. If it's balanced, then the number of levels is log n. But maybe the tree is very long and thin. And then the number of levels is n. If you have random numbers and you put them into a tree, random numbers, you can experiment. You will find that log n, about 2 times log n, is the average length of insert. So usually, when you use a binary tree, you are lucky. Well, there is insert. There is delete, although I don't want to discuss delete. But there is also search. I want to ask, is the number 2.5 in the tree? How do I answer the question? I begin at the root. And I say 2.5. Kana na tau ka kiri. Kiri. Satu. Kana. Satu. Kana. Dua. Kana. It is not here. I never needed to look except at these. I didn't have to check any of these. I only needed to look on one path. Searching is order of log n. This is better than the linked list, where searching you needed to look at every element, order n. This is order of log n. It is faster. It can also be used for sorting. You would call that tree sort. You take your numbers, put them in a tree. That costs about n log n. And then you walk through the tree using a recursive method, and that only takes n. And so the total cost is order of n log n. So tree sort is also usually a good sorting method, n log n. But the tree might not be lucky. Let me see what else I wanted to say about this. Yeah. Because the tree might not be lucky, this is called an unbalanced tree. There are kinds of trees that people have described which are balanced trees. And so the basic idea is this, but there are fancier trees. If you really want to make certain that it is balanced, use red-black trees, but I will not describe them. All right, that is all I want to say about trees. Oh, you can insert anywhere. In the linked list, inserting anywhere, you had to find the place. Here, it is very fast. But there is a faster method than binary trees for searching and inserting, but not for sorting. That's what I want to show you next. And the method I'm going to show you next is called hash tables. Let me try one more time to see if I can get this to work. No. The problem perhaps is that this cord is so long, the signal is so weak that the computer doesn't discover anyone at the other end. Not a problem. All right, hashing. So I'm now going to show you the hash tables. Hash tables are used for inserting and searching not just numbers, but any sort of data. And so the way it works is like this. I build a table. Perhaps it has 8 elements in it, numbered from 0 to 7. In computer science, we like to start counting at 0. And let me put in the following, I'll put in words. And the first word I'm going to put in is ketuhanan. Do you recognize this word?
Yes, of
It is
course.
the first of 5 words we will use.
Yes,
Right? So, we apply some function h to this, and it is a magic function. The way it works, perhaps, is by taking each letter. A letter is represented in the computer by a number. And so, here's a number. Maybe you add this number, add this number, add this number. You add all the numbers. You then divide the answer by 8, the lapan, and the remainder is the h function. And let's say that the answer is 3. What I do then is I put this word here, pointed to by the 3rd element of my table. Now, what is the next in the Panchasila? Kamanusyaan?
Yes.
Let's say 100,000 words, 1,000,000 words, sajuta. So sometimes 2 words will come to the same number. And that will happen when I try karakyata. It gives me the same number as the other one. Not a problem. I can just put it here. And my final one, what's the last one? The second one. And the number I've chosen for that. When I apply the hash function of persatuan, I get enam, and here it is. If the number of elements in my array is the same as the number of words I want to put in, then on the average, each of these lists has length 1. Some lists will be empty. Some lists will have length 1. Some will have length 2. Some might be longer. But on the average, the list has length 1. Therefore, what is the cost of insert? To insert a new word into this list, into this hash table, I must do a calculation. I count that as 1 step. I must find the place in the table and maybe walk to the end. That's average length of list, which is 1, and put it in the end. That's 1. It's order of 1. How hard is it to search? If I am looking, I ask the question, is ketuhanan in my list?
Yes.
Easy. I recalculate this, I get the number, and then I know where to look. And I find it immediately. So, ka'amanan, is it here? Well, we do the calculation, ka'amanan, and perhaps that gives me tujan. I look here and list is empty. Ka'aminan is certainly not in my table. This data structure is used in compilers. When you write a program in C or C++, you have variables. The compiler must remember how you declare the variable. Is this int or float? It remembers that, in a hash table. So every time you use the same identifier, the compiler very quickly finds that identifier along with all the other information that the compiler wants to remember about that identifier. What its type is, perhaps. Have you assigned it a value yet? Different languages have different things they must remember, but these are all remembered in the hash table. Hashing, therefore, has insert, which is very fast, and search, which is very fast. So if you do not need to sort, you only need to insert and search. The hash table is the best organization for you. Questions about hash tables? Maybe if I plug this in, it'll have enough power to find the external monitor. Not yet. Okay, not a problem. I now want to show you a better sorting method. We have seen tree sort and log n. We have seen heap sort and log n. Mathematicians can prove n log n is the best you can do. You cannot do better than n log n. But I will show you something which is better than heap sort, better than tree sort. It is n log n, but if you compare them by writing the program, this one will be faster, a faster n log n. It is called quick sort because it is quick. So the next subject then is quick sort. And I will sort these numbers. We begin by putting those numbers in an array. I want to make sure that I have the same number of numbers as my example here. 2, 6, 5, 3, 5, 8, 9. Okay, I want to sort these numbers. The way I will do it is take the first number and divide all of these numbers into two groups, small numbers and big numbers. Small numbers are those that are this size or smaller. Big numbers are numbers that are bigger than this. So what are the small numbers? Well, Satu is small, 4 is not. Satu is small. Dua, Tiga, and that's all. Those are the small numbers. Now I'll put my starting number there. And now all the other numbers are big numbers. So I will write them down here. These are big numbers. This operation is called partitioning. I partition, that means divide into two groups. I partition the numbers into small and big. If the numbers are sorted eventually, this number is in the right place. Because everything here is smaller, everything here is bigger. This number is finished. But now I have two problems to solve. Sort these and sort these. But those two problems are smaller problems and are independent of each other. Well, how do I sort this? I can use the same method. But with quicksort, if I only have 4 elements, I use a different method. A method that happens to be called insertion sort. Very fast for short arrays. Insertion sort generally is n squared. But for very short arrays, when n is small, it is very fast. And so these numbers I now sort with insertion sort, and they're actually already sorted. Insertion sort is very fast. There's the answer. So these are now sorted, and this is sorted. But these numbers are not yet sorted, and there are many numbers. So I use the same method as before. I take the first one and say, let us partition all of these numbers, those that are smaller and those that are bigger. Which numbers are smaller? There aren't any, okay? Then I put this number down, and everything else is bigger. Sometimes I am not lucky. Now, that divides the problem into the empty problem here, that's easy, and the problem here. I will now solve this problem as a new problem. It is shorter, a little shorter. Take the first element and partition. Well, here's a small number, here's a small number. Here is the partition element, here are the other numbers. I have a small problem and a small problem. I will use insertion sort on both. This is already sorted. Insertion sort will agree. This is insertion sort will very quickly give me the right answer here. And now the entire list is sorted. So now I have the entire list sorted using quicksort. So the algorithm is, if you have a list to sort, if the list is short, use insertion sort. Otherwise, partition the list into two pieces and use quicksort recursively on both sides. This uses recursion. Recursi, recursion. Recursion is when you use the same method on a smaller problem. So again, the method of quicksort is, if the problem is small, use insertion sort. Otherwise, partition, and then quicksort here, quicksort here. How expensive is it? Let me show you with a picture. Let me imagine that I am always very lucky when I partition. Here are my numbers. And when I partition, I divide it nicely in half. So now I have two problems to solve. This problem and this problem. Now maybe this problem here, I am lucky. And when I partition it right in the middle. Maybe on this side also, I am lucky, and I partition it right in the middle. So I have this problem and this problem and this. And at some point, these are so small, I use partition this. I must look at every element once. The cost of partitioning is n. So the amount of work is n work at this level. At this level, I must partition this, and I must partition this. Together, the length of these together is approximately n. So I do n work partitioning at this level. At each level, I am spending that much work. What is the overall cost?